Hello students, so continuing our lectures on quantum mechanics and hydrogen and helium spectrum. So we move on to that discussion, and we assume that there is a two-particle system. Having mass m1 and m2. So total mass is m1 plus m2, and the reduced mass is m1 m2 divided by m1 plus m2. We can write the Schrodinger equation as minus h cross square by 2 capital M del square psi is equal to E psi E dash psi, or we can write minus h cross square by 2 mu if you consider the total particle to be a single particle. Then we will use reduced mass instead, and we will write del square psi is equal to E psi. Now next what we will do, we will write the Schrodinger equation in terms of spherical polar coordinates. So from Cartesian coordinates, that is x, y and z, we move on to spherical polar coordinates r, theta and phi. That means we are now expressing the wave function psi and in terms of r, theta and phi, so which can be written as r function of r and y function of theta and phi. So the Schrodinger equation in spherical polar coordinates can be written as minus h cross square by 2 mu 1 by r square d by dr of r square dr by dr minus ze square by r into r plus h cross square by 2 mu L into L plus 1 divided by r square into r is equal to E r. So we have only taken the real coordinate. This r this represents this part. Now there is a degeneracy involved here, and that degeneracy doing we get number of states having the same energy is given as N is equal to 0 to minus 1, 2L plus 1 here, N, L, M, these are all quantum numbers. So we can represent the wave function psi, which we represent in terms of quantum numbers N, L, and M, is a function of R, theta, and phi, as equal to R and L, R and Y, L, M, theta, phi. They are popularly known as spherical harmonics. So basically, this equation, it forms a Lagrangian differential equation. And we'll use this differential equation to find out the solution, and the solution will come in terms of R and L. So the solutions are represented as R 1, 0. R is a function of 2 into Z by A0 to the power 3 by 2 into e to the power minus rho, and R 2R1 is equal to 1 by 2 root 6 Z by A0 to the power 3 by 2 into rho e to the power minus rho by 2, and R 20 is equal to 1 by 2 root 2 Z by A0 to the power 3 by 2 into e to the power minus rho by R. So now if we plot these functions against R, and so that the radial function has a non-zero value that is equal to 0, and then only for the state. Now the average distance of the electron from the nucleus is 3 by 2 A0. And so plotting the probability of finding the electron with respect to the distance from the nucleus, we find a plot like this for 1s, and will change for other higher states. So this is the probability that the electron will lie between R and R plus dr. And so we can represent this probability Pr dr as equal to R square R to dr. Now the most probable value of R in the one state is A0. A0, and also there are two most probable values of R in the 2s state. So we plot PR dr as we have done earlier. So we are getting, this is for the 1s state, and for the 2s state we are getting a plot like this. So the 2s. So for the 2s state, there are two most probable values of R. So it can be said that if this is the principal contour number, and if L is n minus 1, then there is only one maximum. This implies only one maximum. However, if L is greater than n minus 1, which happens in the case of 2s state, so this is what is happening in the case of 1s state. So here n is equal to 1 and L is equal to 0. So this is the only value. So it is only having one maximum. But in the 2s state, n is equal to 2 and L is greater than 2 minus 1. So in that 2s state, we are getting more than one maximum. More than one maximum. And the maximum value of R is mathematically is always max is equal to n square A0 by Z. And it is observed that L is equal to n minus 1.